Hello everyone, we're going to talk about section 4.2 today, applications of exponential functions. So back in section 4.1 we talked about exponential functions and what they were and how to use them and everything. So this whole chapter is going to be on applying these to just different scenarios and different real life applications. So in many fields we find that a quantity changes at a rate proportional to the quantity present. So this kind of means something along the lines of a population may be increasing at a rate of 1.3% per year. So you're taking whatever percentage your population is at current time, and then you're increasing it by 1.3% every single year. So in cases like this, the amount present at time t is given by an exponential growth function. So we would see that a population in this case will be exponentially growing. Since last year it grew by 1.3%, now it'll grow by another 1.3%. So we continue to have this rapidly increasing rate. And we see here exponential growth functions. Under normal conditions, growth can be described by the function of the form f of t is equal to y naught. So y naught, which we call that y sub 0, with that little 0 that is in the subscript, we call that y naught. So y naught is usually there to represent an initial value, whether that be a population or maybe an initial value of money or something along those lines. But y naught is always just an initial value of something. Then we have e to the kt, or we have f of t is equal to y naught times b to the power of t, where we have that f of t is the amount present at time t, and y naught, or y sub 0, is the amount present at time equals 0, so the initial time when time has not passed at all, our starting value. And k and b are constants that depend on the rate of growth. So when f of t is equal to y naught e to the kt, and k is greater than 0, we describe f of t as modeling exponential growth. And then when k is less than 0, we describe f of t as modeling our exponential decay. And then similarly, when we have f of t is equal to y naught times b to the power of t, and b is greater than 1, we describe f of t as modeling exponential growth. And when b is between 0 and 1, we describe f of t as modeling exponential decay. So these are just two different functions that we use to model exponential growth and exponential decay. In our case, we'll usually be told which one to use and when, or it'll be extremely obvious on which one to use and when. So for example 1 here, which is also checkpoint 1 in your book, we suppose that the number of bacteria in a culture at time t is y is equal to 500 times e to the 0.4 t, where t is measured in hours. So how many bacteria were present initially? So initially, that signifies when time is equal to 0. So let's zoom in a little bit here and we say initially is equal to t equals 0. All right, so if t equals 0, then we're going to use, we have f of t, not f of x, f of t. We're going to use f of t and calculate 500 e to the 0.4 times 0. So since 0.4 is being multiplied by 0, we know that that's going to be 0, and anything to the 0 power is 1, even e, so e to the 0 power will be 1. So we're essentially having 500 times e to the 0, which we know is 1. And our answer is going to be, let's write it down here. Our answer is going to be 500 bacteria. So we know there were initially 500 bacteria. And if you notice, our form here of our equation is 500 times e to the 0.4 t. Well, this is very similar to our equation here that we have right here. F of t is equal to y naught times e to the kt. So in our case, this y naught will be 500, and our k is going to be 0.4. And since k is positive, we know that we're about to figure out that this is going to be an exponentially growing problem. So this is exponential growth since k is positive, and we know our y naught is 500, which we could calculate either way. Now for part B, we have how many bacteria are present after 10 hours. So we're going to use the same function here. We're going to plug in 10 for t. So we have f of t. In our case, our question asks for y, but f of t and y, they mean the exact same thing. F of t just means a function of t, where y inherently means function of whatever variable that you have. So we have f of t is equal to 500 times e to the 0.4, 10 hours, so our time will be 10. So this is technically 500 times e to the, since it's 0.4 times 10, that's like saying e to the 4th power. And take a moment to calculate this on your own if you would like. And if you did, we should have gotten 27,299 bacteria. So we see that our equation here, our function that's representing the number of bacteria in a culture, we see after 10 hours, we're going to have 27,299 bacteria. So we definitely can tell that this function is exponentially growing at a rapid rate, since only after 10 hours we see it increase by that much. All right, for example 2 here, which is going to be checkpoint 2 in your book, we suppose an investment grows exponentially from $500 to $587.12 in 3 years. So we want to find a function in the form of f of t is equal to y naught b to the t power that gives the value of the investment after t years. So now we're going to have to find everything that has to do with this function. So let's start by trying to find our y naught, or our y initial. So we have that our value of investment, let's see, let's look at investment, at our initial time, or t equals 0, is $500, and at 3 years, or t equals 3, is 500. That doesn't look like 500. Nope, that was a year. There we go, $587.12. So now we have these values assigned to different values of t. So we want to solve for, that's a B, nope, for f of 0. So we're solving for that y naught. All right, so all we have to do to solve for y naught is we just plug in 0 for t and see what we end up getting. So we're going to do f of 0 is equal to 500, since we know that at when time equals 0 we have 500. So we know that f of 0 is going to be equal to 500. And if we have f of 0, that means that we have the equation y naught b to the 0 power is equal to 500. Since f of t is y naught b to the t power, and we're replacing t with 0. So this means that y naught b to the 0 power is 500. And since we know that b to the 0 power, anything to the 0 power is 1, this means that we know that y naught is equal to 500. Yeah, I'll write this down here. Y naught is equal to 500. I'll write this in. Since b to the 0 power is equal to 1. All right. So now that we've found what our y naught is, we say now f of t has the form f of t is equal to 500 b to the t power. And now we can solve for t equals 3. Since we know that when t equals 3, we have $587.12. So we can say that since f of 3 is equal to 587.12, this is the same thing as saying 500 b to the 3rd power is equal to 587.12. All right, so now since we found this value, we can start to simplify. So let's divide by 500 on both sides. And this will give us b to the 3rd power is equal to 1.174. And now we want to simplify b, so we just have one value of b instead of b cubed. So what we can do here is we can raise each side to the power of 1/3. And if we do that, we see that our b cubed and our 1/3 are going to cancel, because when you raise a value to another power, and if that value has an exponent, you multiply your exponents to get your final value. So if we multiply 3 by 1/3, they're going to cancel each other out, and we're going to be left with b is equal to 1.174 to the 3rd power, which we can calculate. So feel free to take a moment, calculate this on your own. And we see this is going to be about 1.06. So now that we've found y naught and we found b, we could plug it into our final answer. So our final answer, or our final equation in this case, is going to be f of t is equal to 500 times 1.06 to the t power. All right, so that's our finalized equation. So our equation is in the form of f of t is equal to y naught times b to the t power. Now we can go on to part B, where we ask how much is the investment worth after 10 years. So we're just going to use this equation, and we're going to plug in 10 for t. So we say f of 10 is equal to 500 times 1.06 to the 10th power. So you can feel free to take a second, calculate this on your own. And if you did, you should have gotten $895.42. So we know that after 10 years, our investment will be worth $895.42. So that's how we would go about creating one of these equations from a very minimal amount of information. All right, so now we can move on to example 3 here, which is number 10 in your book. and it is a physical science question. So we have our little description here, which our table shows the atmospheric pressure in millibars at various altitudes in meter. So we have this chart here, and we have altitude starting at 0, we're going up to 10,000 meters, and it looks like our pressure in millibars is definitely decreasing. So for part A is we want to find an exponential function for this data in which t is measured in thousands. So that means that t equals 2 means 2,000 meters. So we're not dealing with t equals 10,000 or 9,000. We're dealing with t equals 9 or 10, along those lines. And we want to set up our problem the same way as we did before. So we want f of t is equal to y naught b to the t power. So we're going to do the same thing as we did before. So first we're going to start with what's our initial value. So we know that when t equals 0, our pressure, or our f of t, is equal to 1,103. Let's replace that t with 0. And let's do our first point and our last point, or our first values and our last values, so we get a good idea of all of the values in between. So we can use a wide range. So we're going to start with 0, and then we're going to do our last one, which in our case is 10. So we'll say, and when t is 10, f of 10 is 265 millibars in our case. All right, so since we found f of 0, we know that our f of 0 equals 1,113. That's the same thing as saying y naught times b to the 0 power is 1,013. B to the 0 power, we know, is just going to be 1. So we get that our y naught is 1,113. So now we have f of t is equal to 1,113 times b to the t power. All right, so now we want to find our value of b. So we're going to plug in our t equals 10 and our f of 10. So f of 10 is equal to 265, and we know that this is going to be equal to 1,113 times b, and in this case t is 10, so we'll have b to the 10th power is equal to 265. And we want to isolate b and simplify it as much as possible, so we're going to divide by 1,013 on both sides here. And we're going to get b to the 10th power is equal to 0.2616. That would be 265 divided by 1,013. So now, since we want to simplify to get to b instead of b to the 10th power, we're going to do the same thing as we did before, and we are going to raise each side to the power of 1 divided by 10. Since these exponents will now cancel and we'll be left with b, we want to find 0.2616 to the 1 divided by 10th power. So you can feel free to take a moment, calculate that on your own. All right, you should have gotten 0.86. So if b is equal to 0.86, we know our final answer. Putting this information all together, we should get the f of t, old habit die hard, f of t is equal to 1,013 times 0.86. 0.86 to the t power. And there's our final answer. That is our final equation for our chart over here. Now part B is we want to estimate 1,500 meters and 11,000 meters, and then we're going to compare with the real values of 846 millibars and 227 millibars. So to do this, we are going to estimate using our equation these values. So if we're using 1,500 meters, that's like saying 1.5. So we're going to do F of 1.5 is equal to our equation, which was 1,113 times 0.86 to the 1.5 power. So feel free to take a moment and calculate this on your own before to pause the video. And you should have gotten 807.9 millibars. And then we want to calculate for 11,000 meters. So we're going to calculate F of 11 is equal to 1,013 times 0.86 to the 11th power. So once again, feel free to take a moment and pause the video if you would like. And you would see that we would get 192.8 millibars. And what this question wants us to do is that it wants us to compare with the real values of 846 millibars and 227 millibars. So by using handy dandy Google, we can find what these values are. So we have our real values. And we see that 846, I'm going to write NB for millibars, is equal to 1,495 meters. And what we were calculating was 1.5 meters, and we ended up with 807.9 millibars, which in the scale of what we're working with is not that far off. So we can see that our equation was pretty generally accurate. And now we want to calculate for 227 millibars. So once again, using the internet. We get that 227 millibars, that looks like 6 millibars, is going to be about 10,976 meters, which we calculated for 11,000 meters, and we can see that 227 and 192.8 are fairly close in the scale that we're working with. So we can see that our equation is fairly accurate. All right. Now we're going to go on to other exponential models. So we need to use different functions if a quantity changes exponentially, but does not grow very large or decrease practically to zero. So these are the equations that we're pretty much used to with exponential functions. We deal with exponential decay or exponential growth, but there are going to be other exponential models that maybe don't decay or grow at certain rates, so we'll need to use different equations. for example 4 here we have, which is checkpoint 3 in your book. We suppose that the value of assets in thousands of a certain company after t years is given by v of t is equal to 100 minus 75 e to the negative 0.2 t. So we ask, what is the initial value of assets? So if we're looking for our initial value, this means that we're going to plug in t equals 0. So initial, oh man, that is the same thing as saying t equals 0. So we're going to plug in t equals 0 for our equation. So we're looking at v of 0 is going to be equal to 100 minus 75 e to the negative 0.2 times 0. We know that negative 0.2 times 0 is going to be 0, so e to the 0 power is going to be 1. So we are essentially left with 100 minus 75, which is 25. So we know our initial value of our assets is going to be 25. This is in thousands, so it would be 25,000. So we want to graph v of t, and we're going to use Desmos to do this. Okay, so now we have graphed our equation, which was y is equal to 100 minus 75 times e to the negative 0.2x, or t in our case, but in Desmos it really likes y and x, so we'll use y and x for now. All right, so we see that this is what our equation is going to look like, and we see that at 0, or y equals 0, we see, not y equals 0, y equals 25, since that was our initial value we had there. We see that that is going to be our y-intercept at 25, so that would be our initial y value. We're looking at this graph, we see that it starts to grow, and then it just stops growing, and just kind of stables off at a certain value, and it looks like it's going to go on to that value for an extremely long period of time. So this is what our graph of this function is going to look like. And part B was just that we needed to graph, but part C is asking us, what is our limiting value of assets? So our limiting value would basically mean what value does our assets kind of just cap at? Like, when does our assets stop growing? What's the limit? And so we can tell by our graph here, at that limiting value, it must be 100, because you see as we kind of follow, we're getting closer and closer and closer to 100, but we'll never actually reach 100. And that means that 100 is going to be our limiting value. And since this isn't 1,000, we know that this is going to be 100,000. So our assets are going to cap at 100,000. So let's go back to our notes. And all we need to do for B was graph. So for part C here, we asked what was our limiting value of assets. So we're definitely going to say our limiting value of assets was $100,000. All right, so we found our limiting value of assets. Now we want to find the value of assets after 10 years. Now, we easily could have found this with our graph. So in answering questions like these, you can use your graph as well, but we're going to calculate it for our purposes of this example. So we want to find the value of our assets after 10 years. So our equation, which was V of t, we're going to say V of 10 is equal to 100 minus 75 e to the negative 0.2 times 10. So we can calculate first what e to the negative 0.2 times 10 would be. You can take a moment to pause and calculate this on your own. And if you had, we would see that we would have gotten 0.135 as our answer. So now we're going to multiply 75 by 0.135. We're going to get 100 minus 10.125. And that was just going to simplify to 89.875. So that's going to be our asset, or our value of assets after 10 years. And since this is 1,000, we know that this is equal to $89,875 after 10 years. All right, so moving on, a variety of activities can be modeled by maybe a logistic function whose rules are of the form f of x is equal to c divided by 1 plus a times e to the kx. So c, a, and k in this equation are all just going to be constants. And our next example is called a forgetting curve. This is also similar to example 6, which is in your book. But our next example will be using this logistic functions. So we have example 5. The amount of U.S. expenditures on national defense in billions of dollars can be approximated by the function f of x is equal to 1,084 divided by 1 plus 1.94 e to the negative 0.171x, where x equals 0 corresponds to the year 2000. So we want to estimate expenditures for year 2005 and 2010. So let's zoom in here a little bit. We want expenditures for years 2005 and 2010. So let's start with 2005. And we'll say x is going to be equal to 5. So what we can do here is we're going to say f of 5 is equal to 1,084 divided by 1 plus 1.94 times e to the negative 0.171 times 5. I encourage you to take a moment and maybe calculate this on your own. And if you had, you should have gotten 593.96. And now we want to calculate for 2010, which is going to be x is equal to 10. So f of 10 is going to be equal to, I made that a little too low, let's just scooch that down. F of 10 is going to be equal to 1,084 divided by 1 plus 1.94 times e to the negative 0.171 times 10. Yeah. So once again, I invite you to take a moment, calculate this number on your own. And if you had, you should have gotten 802.4. All right, so for part B, we're going to assume it stays accurate, and we're going to graph from 2010 to 2020, and we're going to use Desmos. Part C also wants us to use the graph to determine the year in which expenditures will reach 850 billion, and for this, we're going to use Desmos. So when we go to Desmos, we'll be doing both of these things. All right, so using Desmos, we can plug in our equation, which we had was y is equal to 1,084 divided by 1 plus 1.94 e to the negative 0.171x. So when we graph this, we see that this is going to be increasing very fast. It looks like it's going to be a very large equation. So we can kind of zoom out a little bit here. And what we want to find is if we're assuming it stays accurate, we want to graph it from 2010 to 2020. So what we can do here is we can use our little graph settings and we can kind of change our x-axis because we really only care about 10 to 20. So we're going to say 10 to 20. And we can zoom out maybe just a little bit. Maybe we can create lines just so we know where they are. So we can say x equals 10 and x equals 20. And kind of zoom out a little bit. And we see that our graph automatically kind of adjusts itself so that we get a good image between 10 and 20. So between 10 and 20, we see that it is still growing. And now we want to use our graph for part C to determine the year in which our expenditures will reach 850 billion. So what we want to do is create another y value of 850. So we see our line goes through here and it crosses at this point right here, which tells us that we will reach 850 billion in what it looks like 11.4 years. So that means in the year 2011, we will reach $850 million. Now let us write that down in our notes before we forget. All right, so now that we've graphed that in Desmos, we use the graph to determine the year in which expenditures reach 850 billion, and what we found was that expenditures will reach 850 billion in the year 2011. All right, so that concludes our section 4.2. If you have any questions at all, feel free to email me, pop into my office hours, or you can submit an anonymous question if you would like to the online homework form. So please don't hesitate to reach out if you have any questions at all. And I will see you again virtually Monday. Yes, Monday.